Today we're going to continue talking about logic and reasoning, and we're going to look at some of the topics from last week, but in a slightly different light using Venn diagrams. So our warm-up for today is a compound logical statement. We have some premises, which are statements. A is the person is female, B is the person is older than 21, C is the person is older than 60, and D is the person is a teacher. And our compound statement will determine whether or not a person will be invited to a party. So using this compound logical statement, first see, would Mr. Kienoff be invited to the party? And second, would you be invited to the party? So see if you can figure out how to reason through that, and then I'll talk through it with you afterwards. So if you want to pause and try that warm up, go ahead, and then we'll go ahead and talk about it together. So up till now, we've kind of looked at statements like this using truth tables. And truth tables, you've only had to deal with 2 or maybe 3 variable tables. Now, the more variables you have, the more complex these tables get. Since there are A, B, C, and D, 4 variables, we need 2 to the 4th rows because every option has a true and a false. So in a truth table, we're going to have a number of rows equal to 2 to the power of the number of variables. So this has 16 rows within this truth table. So A has half of the options as true and half as false. B also has half and half, but we alternate 4 trues, 4 falses. C, half and half, but it's 2 and 2 and 2 and 2. And D goes back and forth between true and false. So then we see there's a not A and a not C, so we need columns to evaluate those and say if A is this, not A is just the exact opposite. So I made this in Excel and actually used Excel's formulas to say this is literally not A. So whatever was in A, this was the opposite. Same for C, I said this is not C, so it put the opposite value here of what was in this column. Then we have conjunctions and disjunctions to deal with. We want to go from the innermost parenthesis to the outermost. So this A and B is the first thing I want to evaluate. So to evaluate that, again, I used Excel and said and A comma B, meaning it's going to return true only if A and B are both true. So on our first row, we have true, true, and we return true. But down here, we have true, false, and we return false. So this is evaluating whether A and B is true for a given row. Then I have this conjunction evaluated, but I want to see that or that. So I have a disjunction between the thing we just calculated and D. So I made a column for A and B, which is this, or D, which is this. And I said to Excel, tell me, is either of those true? So or G comma D. G is the column right here. I didn't leave the headings. So G is this column of A and B, and it's evaluating is one or both of those true. So where A and B and D were both true, we get a true. D is false and A and B is true, we still get a true, because remember with a disjunction, we only need one or the other thing to be true. So we go through and fill all of those in. Then we go to our next conjunction, not C and B. So this one is looking at column F and B and seeing if they're both true, same exact way we did with this one here. Then we put those two together with a conjunction because there's an and between them. So we say and both of these. So if both of these are true, we get a true here. So true, false gives false, true, true gives true. Then we have our last conjunction, so not A and C is and E and C. So E was our not A column and C was our C column. So we're getting that value there. And then finally, we put an or between these two. So we do a disjunction of the left part and the right part to see if one of them is true. And we end up with 1, 2, 3, 4, 5, 6, 7, I think. 1, 2, 3, 4, 5. 7 options that return all trues. So then I could look at, am I on one of those rows? My result is true. I can even, I showed here in Excel, I could stack all of those together and not make a truth table and do one evaluation with all those things together that will just return the last column. So these compound logic statements, and this is true in programming and computer science as well, you can kind of stack and combine them together to make really complex ideas out of these simple functions of and, or, and not. So next, I want to talk about how we could look at that a little more simply than making that complex truth table. So given these statements, I'm evaluating these specifically for, let me change back to my blue color, especially for me, Mr. K. So I know that I am not female, so not A. I am older than 21, so that's B. I am not older than 60, so that's not C. And I am a teacher, so that's D. Now I can go through, and instead of making an entire truth table, evaluate this compound statement just for these values. So again, I'm going to start from my innermost parentheses here and evaluate A and B. Is that true? Am I both A and B? No, because I have a not A. So this is going to be a false statement. And then I have or D. Is D true? Yes, that is true. Then I have and, not C and B. I am not C and B. Those are both true, so this conjunction is true. Or not A and C. Okay, so I have not A, but not C, so that is a false conjunction because both parts are not true. Now, kind of like order of operations, I'm going to go like left to right when I have these equal symbols. First, I'm going to combine these two. So I have false or true. That evaluates to true because I only need one to be true for a disjunction. Then I have and true or false. So true and true, that one is going to evaluate to true. And then my last thing is true or false, that evaluates to true. So yes, I would be invited to the party, and I did not have to do all of that work of creating the entire truth table, because really I'm only caring about one row from the truth table that's specific to me. Now, if I wanted to evaluate a bunch of different people and see if they would be invited or not, it would be good to have some way to do that with a formula or with a truth table that's going to make that process quicker and not have to repeat these steps every time. Then if you want to see if you would be invited to the party, you could do the same thing. You just have to evaluate these four statements for you, and then go back and plug in those true and false values to get down to one final value of true or false. Would you be invited or not? So if you want to do that, you can pause and go through that for yourself as well. So today's topic, that was kind of just an explanation of compound logic statements, is to talk about how we can represent truth things, like logical things, but with a visual model instead of those truth tables. So this is going to go into our next topic of deductive reasoning, and we're talking about visualizing logic with Venn diagrams. So Venn diagrams, I think hopefully you're familiar with, is when we have circles and we have like possibly some overlap between them, possibly not. So one that I know you're familiar with from 6th grade or from CBE is we have the real number system, which looks something like we usually draw as a big box, and we say this is all real numbers. And then within it, we have two big categories. We have rational and we have irrational. And really, all of them are one or the other, so this empty space between the two circles doesn't really represent anything. There's nothing in that set of numbers because all real numbers have to be one or the other. But then within rational, we have subsets, so within that, we have a circle for integers, and then within that, we have a circle for whole numbers, and then within that, we have a circle for natural numbers. So this is a more complex Venn diagram that shows a relationship between different types of numbers. So if we had a certain number, we could place it in whatever appropriate spot within the diagram there is. And some important things here, we see that all rational numbers can't be irrational. Those two circles are completely separate. There's no overlap like in this little drawing here. And then all of these are sets and subsets of each other to where all natural numbers are whole numbers, and all whole numbers are integers, and all integers are rational. So we don't actually have any in that set like this where there's a partial overlap. So with Venn diagrams, we can represent any of the types of things we've talked about: conjunctions, disjunctions, or conditionals. So conjunctions and disjunctions, if we have two partially overlapping sets, then if we had an and, that would be this region here. So if these are P and Q, this would be P and Q here in the middle in this shared space. If we had over here in just the left side, so let's see, let's shade this. See if you can think about what would be represented by this orange area. It's going to be a conjunction because it's not all of P or all of Q, it's some combination of them. So see if you can think about what that would be. So we know it's in P, but also, and it's not in Q. So that would be represented as P and not Q. Then we could have the same thing over here. The green area would be Q and not P. If we had a simple disjunction of just P or Q, that would be the entire thing of both circles. So P or Q is going to be everything all together, because remember this is P and or Q. Okay, so then let's talk about set the conditionals. So conditionals are going to be more like how these are stacked inside of each other. So if I have this one, which represents, so let's go back to our example from the warm-up. This is people over 60, and then we had in here people over 21. Sorry, I got those exactly backwards. This is over 21, this is over 60. Everyone that's over 60 is also in the set of people over 21. There's no way to get older than 60 without also being older than 21. So this is could be represented as a conditional, and we could say if you are over 60, then you're over 21, because that's impossible to have one without the other. So this would be more of a case that if we had P and Q this way, it would be if P, then Q. Our hypothesis is going to be the subset, and the conclusion is going to be the set around it. So similar here, if you think about numbers, we could have if something is an integer, then it is a rational number, because all integers are rational. But that doesn't necessarily work the other way. Remember, conditionals have a one-way arrow. They don't work in both directions. If we had something that was a biconditional, remember we talked about the other day, P if and only if Q, then that would represent a circle that wouldn't be a very interesting Venn diagram, because we would end up with two exactly identical circles. The two sets would be exactly the same, because every member of one is a member of the other. So this would be P and it would be Q at the same time. There's nothing that belongs to one that doesn't belong to the other. So these are different relationships we could have with Venn diagrams to represent different kind of logic that we've talked about. Let's look at some examples to kind of make this a little more concrete and what some problems like this could look like. So in these, we want to draw a Venn diagram to represent each of these statements. So I'd like you to pause and try to do these, or maybe go through the first one with me and then pause and do the other ones so you can take a shot at these on your own. So the first one says, some students who take, so that's a keyword here, who take choir or chorus also take band. So that means there is an overlap, but not a complete overlap, right? It doesn't say all students who take choir. It says some. So we're going to represent this as one circle for choir. Uh-oh, I missed. And one circle for band. And the overlap we're talking about, the students who take both, would be this region here that they share. Second one says, no perfect squares are prime numbers. So that means we have two completely separate sets. So this is perfect squares, and this one over here would be primes. So two completely separate sets, they don't overlap. This one says numbers divisible by 6 are always divisible by 3. So always denotes a conditional. It means that if a number is divisible by 6, then it is divisible by 3. Yes. So divisible by 3 is our outer set. That's our conclusion. So this is div 3. And then inside of that, we have the numbers that are divisible by 6. So we could write that as a conditional. This is P and Q, and we could say if divisible by 6, then divisible by 3. Next one says every natural number is a whole number. So every, just like always, this goes back to our real number diagram, means that it's a conditional, that it's a strict subset, and the natural numbers must be this smaller set, natural, and then outside of it, we have whole numbers. And with Venn diagrams, the size of the circle is never representative of how many things are in there. Kind of like on the last one, we talked about how in the real numbers, there's nothing in that box that's not in one of the two circles. Likewise here, there's actually only one whole number that's not a natural number, and that is 0. So even though it looks like there's a bunch of space here, that doesn't represent the number of items within that set. Because basically almost all natural numbers, or almost all whole numbers are natural, the only one that's not is 0. Next one says sum, so sum tells us that we're going to have this partial overlap. So we're going to have vertical angles here, vert angles, and then some of them are going to be complementary. So we have this partial overlap of the ones that are both. So specifically, there's only one pair of vertical angles that are complementary, and that would be if we have 45 plus 45 degrees. That would give us complementary vertical angles. And the last one here, irrational numbers are never rational numbers. So we drew that on the last slide, and we said that we have our rational set and our irrational set. And we even said both of those are subsets of the real numbers, which would be a bigger circle or box around both of those. Next, we're going to practice the other way around. We have some pictures. We're going to practice writing the logical statement that this represents. So, same way we just did, but backwards. If you want to pause and try to write these, remember some of our keywords like always or some or never. We're going to be looking to use those words here. So I'm not going to write out all of these, especially because my handwriting is so bad on these, but we're going to say angles that measure 60 degrees are always acute angles. We're going to say all animals that are beagles are dogs. We're going to say some students who play volleyball take piano lessons. So that's these. This one's a little different. So this is no months that start with 31. No, this has some overlap. So this is months with 31 days that don't start with J. So this is basically all of the not January months that start with 31. So this overlap here would be January, and this is all of the 31-day months other than January. So we didn't have one quite like this on the last slide, so this would be all 31-day months that don't start with J. So if this was P and Q, that would be P and not Q. Similar on the next one, we have, this is all the freshmen who don't take art class. And then our last one is all numbers that are multiples of 7 or even numbers. So remember, if this is P and Q, this represents our disjunction of P or Q. Because or is inclusive, it could mean and or. Okay, so a couple more examples for conditionals, since all of those were like conjunctions and disjunctions. We have, if a primate is an ape, then it does not have a tail. So actually same, that's still a disjunction, right? So we have, oh yeah, I need to screenshot. So we have a primate is an ape. So this is ape. And this is no tail. So the reason I included this one, it's an example in the textbook talking about whether we can make deductions or conclusions based on this information. And in this case, we have, it said that Coco is a primate that does not have, wait, Coco, I forget which way it says it. Coco is a primate because this whole box here was primates. That is not an ape. And it was asking, can we draw the conclusion that Coco does not have a tail? Is an ape, does not. So that would mean that Coco could be out here or in here, because all we know is Coco is not an ape. So we can't actually come up with a valid conclusion about whether Coco has a tail or not. And we'll get more into that tomorrow with deductive reasoning. This one, we have people that live in Katy live in Texas. So live in Katy is a P, and live in Texas is a Q. And we have if P, then Q. So that means that we have a conditional of people that live in Texas. And within that, people that live in Katy. And then the last one that says the sidewalk gets wet when it rains. So this one is a conditional, but we've got to be really careful with this one. This one's quite tricky because it doesn't say if P, then Q. It doesn't say if the sidewalk gets wet, then it rains. It's organized backwards, which we do a lot of times in common language, so we have to be really careful with conditionals that we change them to the if-then form and they are in the correct order. So if I wrote, if the sidewalk gets wet, then it rains, that doesn't sound right, that sounds backwards. So this when is telling us this is the triggering event. This is the kind of if or the hypothesis. So that'll be our P, and this will be Q. So we should write it as if the sidewalk, if it rains, then the sidewalk gets wet. Sidewalk gets wet. So not strictly true necessarily, but we're taking it as true here. So we have if it rains, so that's our hypothesis, it goes here, so this is rain. Then outside of that, we have sidewalk gets wet. So sidewalk could get wet in other ways that are not rain, but that's going to be our relationship there. And then the last thing for today, I want to look back at the warm-up one more time. But now that we've talked about Venn diagrams, I want to see if we can represent it as a Venn diagram. If you remember, we had 7 cases on our truth table. So we had 1, 2, 3, 4, 5, 6, 7 cases where this came out to be a true compound statement. This is a Venn diagram that is way more complicated than just 2 circles. This one is set up to evaluate 4 different statements or arguments at the same time. So A is the 2 boxes on the right side, B is the 2 boxes on the bottom. So you see we can have just A, just B, or here A and B. That's like our 2 circles for the Venn diagram. But then we also have C overlapping, so we can have just C, or C and B, or C and A, or here A, B, and C. And then D, similarly, we can have just D or any combination of D with the other things. So we have one box that's all of the things, number 15, that is in the A and the B and the C and the D. So let's go through and use this the way we did our truth table and see if we can use this visual model to represent the logic that we did in the truth table. So we're going to start similarly to what we did before from our innermost parentheses and look for where is A and B. So A, this is just A, this is just B. So the things that are in both the A and B is down here in this box. So A and B is all of these options here. That's where A and B are both true. But we have that or D. So we can also in blue, we're going to make all our blue things this statement, underline all of the things within D, because to satisfy this whole compound argument, it can be either this or that. So we're going to go through and say, okay, these are all of the ones within the green circle that represents D. So all the underlined ones satisfy this blue check mark here. Let's switch to a different color and say, now we're doing and, but let's just do this. So not C and B. So we're going to underline everything that is both not C and B in orange. So not C is not within the yellow, and B is in this bottom half. So this one is in B but not C, and this one is in B but not C, and this one, and those are inside of C, and this one. So these four are in B, but not in C. So now we have a conjunction between those. So that means that in order to fit both of those and make them both true, I'm looking so far at just 5, 13, and 12. So those are the only ones so far that meet everything. Now my last statement has an or, meaning that I'm keeping all three of those answers, or I could have any of these be true, and that's going to also satisfy the whole thing, because it's all of the left part or this part by itself. So I want to highlight in green everything that's not in A and is in C. So we're looking in this yellow bubble in the middle, but not anything on the right side that's in A. So that would be 2, that's in C and not A, 6, 7, and 3. So in total, I ended up with 7 answers, and those 7 correspond exactly to the 7 rows on the truth table that came out to be true as well. So this is kind of a visual model that says, okay, I could have only C be true, or I could have B and C be true, or B, D, and C, or C and D, right? So this is giving me all of my options of people that can attend the party. So now if I took all of my party guests and dropped them into their appropriate spots that they fit within this Venn diagram, I could see visually exactly who gets to go and who doesn't get to go. So as one last step here, let's look at Mr. K was not A, B, not C, and D. So we want to find the spot that represents B and D, but not A and not C. So B is here, D is here, not A and not C would be number 5. So this is where Mr. K is, and that's why I am able to attend the party. So if you place yourself based on your 4 answers, you would be in one of these 16 numbers, and that would determine whether you could attend or not. So that's our notes for today about Venn diagrams. This isn't something that we'll be heavily focusing on or testing. It's kind of like the truth tables and logic stuff before that I said. I think it has a lot of value because these things are kind of at the heart of a lot of stuff with computer science and programming and understanding logical values. So this is more of something I want you just to kind of understand to get how the world works, and less something that we're going to use within geometry. So we will use these ideas, but you'll never have to necessarily draw them as Venn diagrams.